Hello, welcome to my channel. In this video I'm gonna solve practice exercise problem from chapter 3 of Elements of Electromagnetics book by Matthew Sadiku. I'm gonna solve practice exercise problem 3.11, uh, in which we have to determine the Laplacian of scalar fields given below. The scalar field, first scalar field is u equals to x square y plus xyz. The second scalar field, uh, the first scalar field u, the first scalar u, the first scalar field u is in the Cartesian coordinate system, and the second scalar field v is rho z sin phi plus z square cos phi, z square cos square phi plus rho square, which is in cylindrical coordinate system. And the last scalar field f equals to cos theta sin phi ln r plus r square phi. This is in spherical coordinate systems. So we have to find the Laplacian of these three scalar fields in their respective coordinate systems. So before I go to the problem solving part, let's understand what Laplacian is. So let me discuss Laplacian of a scalar field. Laplacian of a scalar field is, given a scalar field V, the divergence of gradient of that scalar is the Laplacian. So it is mathematically expressed by Laplacian of the scalar, which is equal to divergence of gradient of V, the scalar, which is equals to del square V, or nebula square V. So in summary, Laplacian of a scalar is also a scalar. So this is also scalar. So Laplacian of a scalar field measures how much a scalar field differs from its average value in its neighborhood. Laplacian is used to model diffusion, heat conduction, wave propagation, etc. So a scalar field is harmonic if it satisfies Laplace's equation, which is del square V, which is a scalar, equals to 0. And harmonic function is very significant in EMFs and solving EMF related problems, because harmonic function represent steady state distributions of fields, both scalar and vector. And Laplacian operator, which is nabla square or del square. So Laplacian operator is used to describe behavior of a scalar field or scalar fields in relation to divergence and curl. So a very important vector calculus formula, del square V, and the Laplacian operation is very significant in EMF. The Laplacian operator in general, not only Laplacian is used in scalar fields, Laplacian can also be used in vector fields. I'm going to show you that also. So for Laplacian of vectors, given vector A, its Laplacian of vectors is gradient of divergence of the vector minus curl of the vector A. In mathematically, so mathematically it's written like this: Laplacian operator acting upon the vector, which is equals to gradient of divergence of the vector minus curl of the vector A. So Laplacian operator in general describes both scalars and components of vectors. So, and Laplacian also helps solve Poisson's equation, which is a more general form of Laplace's equation. Poisson's equation is described by this. uh, the Laplacian operator acting upon scalar equals to f. F is a source. So the functions that satisfy Poisson's equation are source driven functions, and the harmonic functions, or the functions that satisfy Laplace's equation, are source free functions. For example, Laplacian operator acting upon scalar potential VE is equals to gradient of the vector E, electric field intensity, which is equals to rho v by epsilon in general, where rho v is volume charge density by epsilon, which is electric permittivity. And Laplacian operator on vector A is equals to vector A here is magnetic vector potential, which is equals to del operator cross B. B is magnetic flux density, which is equals to curl of vector A, which is magnetic vector potential, which is equals to mu J. J is current density and mu is permeability. This is almost all about Laplacian of vectors and scalars. Before solving, let's describe the Laplacian operation in the respective coordinate systems. So Laplacian operation in the respective coordinate systems is expressed like this. So in Cartesian system, the operation looks like this. In cylindrical coordinate system, the Laplacian operation looks like this, and in spherical coordinate system, this whole big operation. So now let's go to the problem solving part. Let's directly use this formula and get the result. So our first scalar field is u equals to x square y plus xyz. Now we just have to take Laplacian of this vector. So we have to take Laplacian of the scalar field. So nabla operator or del operator acting on the scalar field u, which is this. So now in terms of x is 2xy plus yz, plus in terms of y is x square plus xz, plus z is in terms of z, so here 0 plus xy. Now again the partial differentiation. So in terms of x is 2y plus 0 plus 0 plus 0 plus here also 0. So answer is 2y. So this is the Laplacian of the scalar field u equals to x square y plus xyz, the Laplacian of which is 2y. So this is our second scalar field, which is in cylindrical coordinate system. So Laplacian of this is Laplacian operator acting on the scalar field v. So in cylindrical coordinate system, the formula is 1 by rho. So this is the formula in cylindrical coordinate systems. Now we just have to directly take the value. So partial differentiation in terms of rho of the scalar field. So here is z sine phi. So rho z sine phi, this is 0 plus 2 rho, this is 1, and 1 by rho square, so say phi rho z cos phi plus, so 2z square cos phi cross minus sine phi plus 0. So this is the main part. Now partial differentiation with respect to z, so rho sine phi plus, so 2z 2z cos square phi and 0. So now, so if we do the second differentiation with respect to rho, so 1 by rho, this will be z sine phi plus 4 rho. So rho cross rho square, so 4 rho, uh, this, and 1 by rho square. So partial differentiation with respect to phi of this part is this, so rho z minus sine phi minus 2z square cos 2 phi, so 2 cos phi sine phi is sine 2 phi, and partial differentiation of sine 2 phi is 2 cos 2 phi. So I have just written it directly, no extra lines, so plus partial differentiation again, so this is 0 plus 2 cos square phi. So now the final answer is 4 plus z by rho sine phi minus z by rho sine phi minus 2z square by rho square cos 2 phi plus 2 cos square phi. Thus this and this cuts out, so 4 minus 2z square by rho square cos 2 phi plus 2 cos square phi. So this is the answer, this is the Laplacian of the scalar field, this which is in cylindrical coordinate system. So Laplacian of the scalar field v is 4 minus 2z square by rho square cos 2 phi plus 2 cos square phi. This is the answer. This is our third and last scalar field, of which we have to take Laplacian. So Laplacian operator, this is in spherical coordinate system, so Laplacian operator will be in also, will also be in spherical coordinate system. So the formula of Laplacian in spherical coordinate system is 1 by r square partial differentiation r square. So this is our Laplacian in spherical coordinate systems. Now if we just take the, so I'm not gonna write any extra lines, I'm just gonna straight write the partial differentiation. So 1 by r squared, so here the second partial differentiation, and here is r squared, so partial differentiation in terms of r of the scalar field, so in terms of r, so cos theta sin phi by r plus 2r phi by 1 by r square sin theta, partial differentiation in terms of theta. So sin theta and partial differentiation in terms of theta is here is cos theta, so there will be minus sin theta, so minus sin theta sin phi plus 0. So this is 0, there's no theta component, so only minus sin theta sin phi ln r, sorry, ln r plus 0. Now plus, so this 1 by r square sin square theta, r square sin square theta, we will do this double partial differentiation in parts. So second partial differentiation, right? So first partial differentiation in terms of phi gives cos theta cos phi plus r squared. Now so 1 by r square, so if we take the partial differentiation with respect to r straight directly, so uh, cos theta sin phi plus, so here is 2 r cube phi, so 6 r square phi. So this is the first 1 by r square sin theta. So second partial differentiation with respect to theta. So if we take the minus out of the bracket, it will be, so minus 1 by r square sin theta, and partial differentiation with respect to theta is, so sin square theta, so 2 sin theta cos theta sin phi ln r plus, so here it will be plus 1 by r square sin square theta, so here del by del phi, so partial differentiation with respect to phi, so cos theta minus sin phi, so I have forgot to write ln r, so ln r plus 0. Now lastly cos theta sin phi by r square plus 6 phi minus, so here 2 sin cut out, so 2 cos theta sin phi ln r by r square. Now here also is a minus, so minus cos theta sin phi ln r, cos theta sin phi ln r by r square sin square theta. So here we have common in the three parts, so cos theta sin phi by r square is common in these three parts of the result. So if we take the common out, so 1 by r square cos theta sin phi, so in the brackets it will be 1 minus 2 ln r minus ln r by sin square theta plus 6 phi, so 6 phi. So this is the answer. So this is the Laplacian of the vector, so this is the Laplacian of the scalar field f, which is in spherical coordinate system. So that's it. I hope you have understood my uh, explanation of the Laplacian operation, and the problem solving part. I hope you have understood the calculations. So thank you for watching this far, and if I have any mistakes, let me know, and subscribe to my channel. Thank you.